There's a spot on the moon where sunlight has never touched the ground. Not once. Not in all of history. That should give you pause for a second, because we're not talking about a cave or some patch of darkness that comes and goes with the seasons. These are craters near the lunar poles, and thanks to the way the solar system is set up, they live in endless night. They're ancient, untouched, and brutally cold. Scientists call them permanently shadowed regions, but honestly, that's underselling it. The truth is, these patches of frozen darkness might be the most valuable real estate anywhere in the solar system. And right now, two of the world's superpowers are locked in a quiet, high-stakes race to control them. This isn't some wild guess. The money's already on the table. The missions are moving forward. And no, it's not just about scientific curiosity, not when this much is riding on the outcome. But let's not get ahead of ourselves. Before we jump into the politics, there's a more basic question. Why do these frozen craters exist at all? And why did it take so long for scientists to wrap their heads around them? Most people think of the moon as a dead place. No weather, no oceans, barely any atmosphere. It's a vacuum, almost more like a piece of lab equipment than a world. And in those conditions, with the sun blasting down and no air to hold anything in water, shouldn't stand a chance. The sunlight should tear it apart. The vacuum should yank it away. Simple physics says that if you dropped a water molecule on the moon, it wouldn't last more than a few hours. So when scientists started picking up hints that there was water on the moon, excitement wasn't the first reaction, it was doubt. For years, every sign of water got chalked up to something else. Bad data, contaminated samples, instrument glitches. The idea that the moon was bone dry was so baked in that finding water there felt as likely as finding ice cubes in an oven. People just went with the easier answer. But this is where things start to get weird, in a good way. Back in 1976, the Soviet Luna 24 probe drilled into the moon's dusty surface and brought some of it back to Earth. When scientists checked it out, they found something nobody expected. Water. About 0.1% by mass, and there was even more in the deeper layers. People noticed, argued a bit, then shrugged it off. Probably just contaminated, they said. After all, Earth's air is full of moisture, and it's easy to mess up a sample without realizing it. The dry moon idea survived. Then, in 1994, NASA's Clementine spacecraft changed everything. It mapped the whole lunar surface, and the data from the poles caught everyone's attention. Clementine found that some craters near the poles never see sunlight. The moon only tilts about 1.5 degrees, nothing compared to Earth's 23, so at the poles, the sun just crawls along the horizon. The crater rims are high enough to block it out completely. In some places, the sun hasn't touched the ground for billions of years. Anything that fell in any molecule, any bit of material, could have just stayed there, frozen solid, waiting since before there was life on Earth. Here's what most people miss. The moon doesn't hold onto water because it's damp. It keeps it because it's cold, and only in these exact, rare places. These craters act as natural deep freeze lockers. No sunlight, no atmosphere, just endless cold. The temperatures in there aren't just low, they're in a class of their own. We'll talk about just how cold in a bit, but the point is, once scientists saw what Clementine found, the search for lunar water got real. It wasn't just a theory anymore. People started looking for proof. NASA sent up Lunar Prospector in 1998 with a neutron spectrometer built to sniff out hydrogen, the telltale sign of water if you find it in the right amounts. Prospector picked up strong hydrogen signals at both poles. The numbers were wild. Those shadowed craters might hold anywhere from 10 million to 300 million tons of water ice. Sure, that's a huge range, nobody's pretending there isn't a lot we don't know. But even at the low end, it was enough to turn the whole conversation upside down. Here's the thing. Just finding hydrogen on the moon didn't settle the water question. Hydrogen shows up in other stuff too, like hydroxyl, which is OH, not H2O. So, to really see if there was water, mission planners went for something bold. When Lunar Prospector's mission wrapped up in 1999, they steered it right into a crater at the moon's south pole. The hope? That the crash would kick up a plume of debris. If there was ice hidden down there, telescopes on Earth would spot water vapor drifting above the rim. Nothing. No water signature at all. The crater just swallowed the impact and stayed silent. Japan tried their own version in 2007 with the Kaguya orbiter, ending its run in a similar crash landing near the pole. Same story, no clear sign of water in the material thrown up. Each experiment nudged the evidence a little further, but never quite far enough. It was maddening, honestly, like chasing a mystery where every clue led to another locked door. Then in 2008, the door cracked open. India's Chandrayaan. One spacecraft sent a probe down toward Shackleton Crater at the South Pole. As it fell, its mass spectrometer tasted the thin, almost ghostly lunar exosphere, the wispy layer of molecules clinging to the surface, and finally caught water molecules. Meanwhile, the orbiter circling above carried NASA's Moon Mineralogy Mapper, which picked up water and hydroxyl signatures on the surface from orbit. For the first time, water wasn't just a statistical blip, it was a real spectroscopic fingerprint. Even more surprising, they found traces not only in the shadowed craters, but right out in the sunlit soil. That part's pretty weird when you think about it. Sunlit lunar soil gets hammered by solar radiation and sits exposed to space. Water shouldn't survive there, but now scientists think the moon has its own fleeting, subtle water cycle. Solar wind slams hydrogen into the soil, it reacts with oxygen, and for a brief window, maybe just during the cold lunar night, water molecules hang around before vanishing again at lunar noon. It's not liquid, it doesn't flow. It's nothing like Earth's water cycle. Still, it means the moon's surface is more chemically alive than anyone guessed. That actually matters a lot more than it sounds. We'll circle back to that. Then came the moment everyone had been waiting for. 2009. NASA launched LCROSS along with the bigger Lunar Reconnaissance Orbiter. LCROSS pulled off something almost theatrical. Instead of discarding its spent upper rocket stage, the team used it as a battering ram, 2.3 tons of hardware, aimed straight at Cabeus Crater near the South Pole, one of the coldest, darkest spots on the moon. This time, the results were crystal clear. The crash sent up a plume of debris into sunlight, and LCROSS's instruments caught water vapor, hydrogen, ammonia, methane, carbon monoxide, and carbon dioxide, all of it trapped in the frozen soil, locked away in darkness for who knows how long. The hydrogen signal prospector picked up years before? It was water ice after all. Shackleton, Cabeus, and other craters like them held ice mixed into their soil, along with other buried volatiles. Now, scientists figure the moon's permanently shadowed regions hide about 600 million tons of water ice. Imagine half the volume of Lake Travis in Texas, but instead of a lake, it's scattered in frozen grains across a landscape the size of a small continent. Most of it is at the South Pole, though the North holds some too. It's not like digging up big, pure blocks of ice. Either it's all tangled up in the regolith, those frozen molecules wedged between ancient dust grains, buried beneath a blanket of powder from billions of years of micrometeorite hits. Getting it out won't be simple. None of this has been simple. And here's where things get really strange. The same craters that hoard the moon's ice also serve up some of the most brutal, unforgiving conditions anywhere in the solar system. No exaggeration, these places are about as hostile as it gets. Let's start with temperature. The Lunar Reconnaissance Orbiter carries a thermal sensor called Diviner, which has mapped out the polar craters on the moon in incredible detail. What Diviner found surprised everyone. In some of these craters, the temperature at the bottom drops to just 25 Kelvin. That's about minus 415 degrees Fahrenheit. To put that in perspective, Pluto, way out there on the edge of the solar system, averages around 40 Kelvin. So, the floors of these lunar craters are even colder than Pluto. Honestly, they're some of the coldest natural places we know about anywhere in the solar system, just a few degrees above absolute zero. That's as cold as physics says things can get. At those temperatures, regular spacecraft fuel doesn't just freeze, it stops being fuel. Lubricants turn rock solid. Batteries lose their charge entirely. Materials that bend and flex on Earth become so fragile they can snap like glass. Electronics? They start acting weird, because as you approach absolute zero, circuits don't behave the way their designers expect. They do things nobody quite planned for. So, any rover, drill, or instrument you send down into those shadows runs into problems that don't even show up in standard engineering textbooks. Now, add darkness to the mix. Not just a dark room where your eyes adjust after a while. This is total geological darkness. The sun hasn't touched these crater floors in billions of years. Even the faint scattered light from the rest of the moon barely reaches them. To see anything at all, the Lunar Reconnaissance Orbiter uses an instrument called shadow cam. It's built specifically to capture images using just the faintest light-reflected starlight and earthshine, which is sunlight bouncing off Earth. Shadow cam has managed to get pictures sharp enough to spot slopes, boulders, and maybe even patches of frost. But it took a camera specially engineered to see in light hundreds of times dimmer than what a regular camera can handle. If you're working on the crater floor, you're basically working blind. Solar panels? Forget it. Anything that needs sunlight for power is out. Engineers are coming up with nuclear heaters, radioisotope power sources, and beefed-up batteries that can handle the cold. Even then, the real test isn't if the machines work in theory. It's if they can survive the sudden shift from the sunlit rim, where things are warmer, down into the frozen heart of the crater. And then there's the dust. Every Apollo astronaut there were 12, who walked on the moon, came back complaining about eye and lung irritation from lunar dust. At the time, people shrugged it off as a minor annoyance, just something extra to deal with on top of all the other dangers. Looking back, that might have been the biggest warning they could have given us. Lunar dust isn't like any dust on Earth. Here, wind and water grind down sharp edges, smoothing glassy fragments into something closer to sand a little easier for our bodies to handle. On the moon, there's no wind or rain. For billions of years, only meteoroids and micrometeorites have been hitting the surface, smashing rocks into powder. The result? Particles so fine they look like shattered glass under a microscope. Sharp, jagged, irregular. And because nothing ever washes them, they're chemically active, their surfaces fresh from constant radiation, coated in compounds our immune systems have never seen and aren't built to deal with. When the Apollo crews brought lunar dust back into their capsules, and they couldn't avoid it, since the dust stuck to everything thanks to static electricity, they said it smelled like gunpowder. It got everywhere. It scratched up their helmet visors, jammed mechanical joints, wore down the shiny coating on their suits. Those were just the immediate, mechanical headaches. The real biological risk? People didn't understand it well back then, and honestly, we still don't have all the answers today. Scientists have exposed human lung cells and mouse brain cells to fake lunar dust in the lab, and the results are pretty unsettling. The tiniest bits of this dust particles so small you can't see them killed off up to 90% of the cells in these tests within just a day. What's happening here? It looks like a combination of damage from the dust's sharp edges and toxic reactions from chemicals on its surface. In rats, breathing in lunar dust led to lung inflammation that only got worse the longer the exposure lasted, especially over a 1-3-week stretch. Here's the really worrying part. In animal studies, the smallest dust particles didn't just stop at the lungs. They made their way from the nose straight into the brain, riding along the olfactory nerves and dodging the body's usual defenses that keep the brain safe. We still don't know for sure if this same shortcut to the brain would happen in people. No one's done those experiments, and, honestly, we haven't had humans living on the moon long enough to find out. But the direction this research is heading is hard to ignore. NASA scientists have said, point blank, that lunar dust could be the biggest everyday health challenge facing future astronauts. Not some sudden disaster like a rocket explosion or a systems failure, but a slow, sneaky, long-term threat. It's the kind of thing that builds up quietly until it's just too big to ignore. The Apollo astronauts mostly just got hit with a quick, intense bout of lunar hay fever. But a permanent base would mean people breathing in dust for days, weeks, even months, no matter how careful everyone is. The problem is, lunar dust is electrically charged, so it sticks like crazy to everything: spacesuits, tools, equipment. It sneaks into habitats through airlocks and little seams, no matter how well you try to seal them up. This dust problem has basically spawned its own branch of engineering. New lunar outpost designs focus on keeping dust out in the first place, because once those fine particles get inside, getting rid of them before someone breathes them in is almost impossible. Engineers have even built active dust shields that use electric fields to push charged dust away from things like cameras, solar panels, and radiators. In 2025, on a commercial moon mission, one of these shields actually worked. It cleared dust from key surfaces right there on the lunar surface. But does it work well enough? For long enough? And on a big enough scale? That's still an open question. And this is where the real stakes of the lunar South Pole come into focus. Down at the moon's South Pole sits something that could change everything about space exploration. Water, ice. If we can split that ice, we get hydrogen and oxygen for air, water, and rocket fuel right on the moon. No need to haul it up from Earth at a huge cost. Every ton of water made on the moon saves several tons of launch mass from Earth. Considering that every kilo launched into space costs thousands of dollars, a steady, large supply of lunar water could totally change what's possible. Not just lunar bases, think fuel stops for Mars missions, or supply depots for all kinds of activity as humans start spreading out across the inner solar system. Water is the foundation. If you control the water, you control the logistics of everything that follows. That's why the race to the lunar South Pole isn't just about science. Sure, the science is fascinating. The ice in those craters could be a time capsule from the early solar system, maybe even holding clues about how Earth got its water. Planetary scientists could spend decades digging through what's buried there. But the reason governments are spending big, setting deadlines, and watching each other so closely, it's all about strategy. The US, through the Artemis program, has set its sights right on the lunar South Pole for the next crewed landing. Artemis III, which aims to put astronauts back on the moon for the first time since 1972, has picked landing spots near Shackleton Crater as top choices. If everything stays on schedule, that landing could happen sometime in the latter half of the 2020s. The plan is to build a small outpost on a ridge that gets sunlight, right next to the permanently shadowed craters where the ice sits close enough to reach the ice, but high enough to stay powered and avoid brutal cold. It's a spot where astronauts can work, robots can drill, and the first steps toward extracting and using lunar water can actually happen. What really makes these ridges special is something that almost feels like cheating. Near Shackleton Crater, certain high spots, rims, and peaks soak up sunlight nearly all the time. They only slip into shadow for a few hours each month. That's because, at the lunar poles, the sun just hovers along the horizon, so if you're on the right elevated ground, you catch its rays almost non-stop. People call these places peaks of eternal light. If you want to set up shop on the moon, these are the spots you want. They're sunlit, not quite warm, but much less brutal than the crater floor, about -60 degrees Fahrenheit instead of -400, and they're right next to ice deposits. There aren't many of these ridges. Their geography is rare and very specific. China sees the same thing. Their lunar program, under the banner of the International Lunar Research Station, has laid out a series of robotic missions aimed at the South Pole through the late 2020s. They've already brought back samples from the far side. Next up, they're sending a mission with instruments designed to hunt for water ice in the moon's permanently shadowed areas and to study what it's like down there. After that, they plan to test ways of using local materials like 3D printing with lunar regolith to start building structures right on the moon instead of shipping everything from Earth. By the early 2030s, their roadmap calls for permanent robots at the South Pole, with astronauts to follow. Russia, technically China's partner, hit a setback in 2023 when their Luna 25 spacecraft crashed during landing. Right now, Russia's part in this race looks pretty uncertain. India, on the other hand, landed a rover near the South Pole in 2023 and wants to go after the ice directly in future missions. Japan and the European Space Agency are both getting in on polar exploration too, usually teaming up with either the US or China. Meanwhile, private companies are entering the scene, betting on the idea that lunar ice mining could turn into a real business, selling water and rocket fuel to space missions in need of a refill. The head of NASA hasn't been shy about his worry. China could get to the South Pole first and grab the best ground, the highest peaks, the sunniest spots, the easiest access to ice just by being there. No treaty, no international law, just first come, first served. Once someone puts down infrastructure, everyone else has to work around it. Officially, China says its program is scientific and open to partners. Whether that's genuine or just good PR, well, that's up for debate. Legally, this whole situation is a mess. The Outer Space Treaty from 1967 says no country can own the moon or any other celestial body, but it's fuzzy on resource extraction and doesn't really address the fact that once you build something on a patch of lunar ground, you pretty much control it, treaty or not. The Artemis Accords, a set of agreements the US has signed with dozens of countries, try to set some rules about using resources and creating safety zones around lunar operations. But China and Russia haven't signed on. So, the accords help, but they don't cover the players who matter most in this race. Bottom line, there aren't many perfect sites at the South Pole. The geography is tight. Only a handful of peaks sit next to ice-rich craters, and when you add in the need for safe landings and constant sunlight, the list shrinks even more. Whoever gets there first and builds something doesn't just set up shop for themselves, they shape the environment everyone else has to deal with. You don't need to plant a flag or claim the moon. You just need to show up in the right place first, with equipment that works. That's how you win. This is the real race, not planting a flag for show, not just being the first to do science. It's about getting working infrastructure to the most valuable spots before anyone else, and then building out from there while the window's still open. There's this weird twist in all of it. The things that make those permanently shadowed places brutal, the pitch-black darkness, ridiculous cold, how untouched and ancient they are, those are exactly why they matter so much. The darkness kept the ice safe. The cold kept it solid for billions of years. No sunlight means the stuff trapped there hasn't changed. The hardest, most unforgiving place on the moon? That's where the real prizes are. The dust tells the same story in its own way. The moon's surface has taken a beating for billions of years, and now we have this regolith super abrasive, a nightmare for engineers. It's dangerous in ways nobody really saw coming, even after Apollo. But look at it another way. It's also a resource. You can sinter regolith, fuse it, 3D, print it into walls. The same stuff that'll wreck your lungs and jam your gear could, with the right tech, become the bones of a lunar shelter. That's the irony here. The moon's biggest hazard is also the raw material for staying there. So, what does all this mean? The moon isn't just some science project or a distant memory from the 60s. It's a resource, and we're at the starting line of a long, high-stakes contest, economic, political, maybe more. Whoever gets there first, whoever builds real infrastructure that actually works, sets the stage not just for lunar operations but for humanity's whole push into the rest of space. The moon isn't the destination, it's the doorway, and the water at its poles is the key that unlocks it. Most people still see the moon as something NASA checked off its list decades ago. Like the story ended. As if the main thing was just that we made it there and back. But Apollo barely touched what the moon really is. A dozen people walked around, grabbed some rocks, did a few experiments, planted a flag, and left. Then, for 50 years, the moon just kind of hung out on the edge of our imagination, something finished, not something waiting. Now, things are different. The new missions headed for the South Pole aren't about proving we can get there. They're about finding out if we can use what's there to go farther. Can we turn that ancient ice into the fuel that gets people to Mars? Can the most hostile place on the moon become the foundation for everything that comes next? Nobody knows yet. We haven't shown we can mine and process lunar ice on a big scale. The machines that can handle those deep freeze craters aren't ready for real-world tests yet. The dust control tech needed for a long-term base is still in the works. Who gets to dig up what, and under what rules, is still a fight waiting to happen. Every piece of this is still up for grabs. You can see where all this is headed. The rush is real. Two big players are charging ahead, side by side, aiming for the same spot, both calling their shots in no uncertain terms. That alone says a lot about the stakes. Before we wrap up, there's one last thing to think about. Some parts of the moon never see sunlight. People call these areas time capsules, places frozen since the solar system was young. Inside those craters, you'll find volatile compounds, maybe even organic molecules left behind by comets that smashed into the moon billions of years ago. Some of those same comets probably hit Earth too. It's possible that the building blocks of life, the stuff that made biology possible, came here from space. If so, the moon's polar craters could hold a snapshot of what those molecules looked like before Earth's living systems changed them forever. We haven't dug up that record yet. Nobody's studied it. Whatever secrets those craters hold are still locked away, frozen, and untouched. Sure, the race to the lunar South Pole is about water and power, but it's also, whether anyone planned it or not, a race to crack open the best archive of early solar system chemistry we've got. What we discover there might finally answer how Earth became Earth, and if the same magic could happen somewhere else. That's the big question. And honestly, it's the one nobody's really tackled yet, not in any mission blueprint, not in any political strategy, not in the engineering specs. If that ice reveals what we think it will, the story doesn't end on the moon. It doesn't end anywhere we can see.